Hello, everyone. I'm Justin Moresco, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on FEMA P-2139, Short Period Building Collapse Performance and Recommendations for Improving Seismic Design. This webinar is brought to you by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency. If you haven't already, you can download the webinar handouts using the link provided in the chat window in the Zoom control panel. We know that many of you are interested in receiving professional development hours for your attendance today. For those who registered and attend the webinar, a certificate documenting professional development hours will be sent by email within 4 weeks. If at any time during the webinar you have questions, please type them in the question and answer window in the Zoom control panel. We'll not be having a live question and answer session during this webinar, but after the webinar, we'll provide all registered participants with written responses to all the technical questions that we received today. I'd now like to turn it over to Mike Tong, who will provide a brief introduction to today's webinar. Mike is a physical scientist at FEMA's National Earthquake Hazards Reduction Program. He served as the project officer overseeing the FEMA-supported ATC project that led to the publication of FEMA P-2139 report series. Mike, please go ahead.
Thanks, Justin. Welcome everybody to attend this ATC webinar on short period buildings, collapse performance, and recommendations for improving seismic design. This webinar is intended to present the technical information in a series of 4 FEMA reports, also known as the FEMA P-2139. The reports are available at ATC and the FEMA websites for free download. The reports collectively provide the findings and recommendations into a well-known short period building seismic performance paradox. Simply put it, short period buildings are analytically predicted to have higher collapse risks under strong earthquakes. However, past earthquake damage information didn't show higher collapse rates for short period buildings. This paradox is known for decades and more quantitatively studied in recent years. FEMA funded the ATC project on this issue for 2 reasons. One, the predicted collapse risks is exceeding the ASC 7 target seismic performance criterion for new buildings, namely less than 10% probability of collapse at maximum considered earthquake. Second, the issue appears to be across all building types and materials. So after multi-years continued effort, ATC project team has successfully resolved the issue and developed a solution methodology along with their findings, conclusions, and recommendations. So in today's webinar, we're going to learn all about it. Going forward, we're looking forward to work with the engineering community to introduce and implement the recommendations in seismic codes and design practices. I'd like to take this opportunity on behalf of the FEMA NEHRP, National Earthquake Hazard Reduction Program, to thank ATC, the entire project team, and the project review panel for the persistent effort and successful completion of the project. And I'd also like to thank Charlie Kircher, Kathy Colbean, Justin Moresco, and Gigi Grosjean for preparing, organizing, and delivering this webinar to a broad audience. So with that, I'll pass it back to Justin to get it started. Justin, go back to you.
Thank you, Mike. So now let me tell you about your presenters today. Charlie Kircher is a principal of Kircher & Associates in Palo Alto, California, and has more than 40 years of experience in earthquake engineering, focusing on vulnerability assessment, risk analysis, and innovative design solutions. He's a fellow of the Structural Engineers Association of California and was elected to the National Academy of Engineering in 2019. Charlie was the project technical director for the ATC project that led to the publication of the FEMA P-2139 report series. Kelly Cobean is a principal with Wiss Janie Elsner Associates in their San Francisco office and has more than 30 years of experience on a wide range of project types, sizes, and construction materials, with a special interest in seismic resistance of light frame construction. She's been involved in numerous code development, research, and educational activities, including updates to the NEHRP recommended provisions for seismic regulations for new buildings and the ASC 7 seismic provisions. Kelly was a member of the project technical committee for the ATC project that led to the publication of the FEMA P-2139 report series. I'd now like to turn the webinar over to Charlie. Charlie, please go ahead.
Thank you, Justin, and thank you, Mike and everybody. As Mike just said, encapsulating this question of the short period building paradox as a question, why do analytical models of code-compliant designs predict high probabilities of collapse for short period buildings contrary to damage observed in actual earthquakes and the judgment of earthquake engineers? This is, in essence, the question we are answering with this project. As an example of the basis for this question is a figure taken from a NIST study in 2012, which looked into recasting the framework of seismic codes and investigated short period buildings as part of that study, and compiled at that time what was available in terms of collapse studies using P695 methodology, as shown in this figure. And what we saw in this figure, which bothered us a lot, was that short period buildings seem to have a tendency to exceed 10% probability of collapse given maximum considered earthquake ground motions, and that 10% is considered to be the acceptable limit of codes. We thought it shouldn't just be less than 10%, it should be something more like 2 or 5%. And this is the genesis of the project. Why does this matter? Well, there's a lot of short period buildings out there. They're the vast majority of all buildings. When we talk about short period buildings, we think of them as having a period of less than about a half second and perhaps story heights of 1 to 5 stories. The concerns we have are these buildings actually meeting the collapse objectives of the seismic codes? That means they should be less than 10% or lower in terms of their collapse probabilities. Are improvements in the seismic building codes design and assessment methodologies warranted? That is there something we should do different for these types of buildings? This led to the study. It began in 2013. It was continued through 2020 for 7 years. Yipes, 7 years. FEMA-funded project. It was conducted by ATC. It produced the 4 reports Mike mentioned. 1 report for each of the 3 systems, seismic force-resisting systems that we studied individually, and 1 collective report containing the overarching findings. I'll be speaking mainly to the overarching findings common to all 3 systems. Again, if you're interested, these reports are available. I cannot do justice to 7 years of research and 4 very thick reports in 1 hour. So anything that doesn't come through fully, be sure and get yourself a copy of one of these reports. This is the cover of the first report and identifies members of the various teams that participated. Thanks to all, I won't be able to actually go through this list and individually, but there was suffice it to say, there was a large number of contributors to these projects. Objectives. We want to identify the root cause of the short period building paradox. And, do we have the models wrong? If not, what can we do about fixing these models of these buildings? We want, and accordingly, we want to improve and validate the numerical modeling methods for short period buildings. And out of this, we want to develop any recommendations for improving seismic codes and engineering practice for future code initiatives. So we want to make some use of this in terms of seismic codes and seismic design. Along the way, we realized that we thought we knew what happened in earthquakes, but we wanted to take other studies, but we wanted to take a harder look at actual performance observed in past earthquakes. So we looked at a number of different earthquakes, both in the U.S. and outside of the U.S. We also are informed by full-scale shake table testing at such facilities as the E-Defense facility in Japan, in Miki, Japan, and at the University of Buffalo and the University of San Diego. These are very important studies, but they're very difficult to do and very limited, therefore. Selection of systems. We had to decide which systems to look at, which systems are commonly used for short period buildings. The most commonly used building is wood. It represents probably about 75% by square footage of all short period buildings. After that, the next most used system is reinforced masonry. So those two are on the list. The third system we selected was steel braced frames because we were already looking at walled systems, and steel braced frames are also commonly used for short period buildings. So we ended up with these three systems: wood-like frame, reinforced masonry, and steel braced frame, which represent more than 85% of all the square footage of low-rise occupancies. So, little cartoons of our three systems, archetypes of our three systems. It was a very involved process, deliberate and involved process to go from first selecting representative archetypes to actually getting probabilities of collapse. So let me kind of give you an overview of this process. First step, we have to identify the archetypes. What is a typical wood building for a low-rise wood building? What's a typical masonry building? What's a typical steel building? Once we get the archetypes selected, we then are they are designed, in this case by structural engineers who design these sort of buildings. The next phase of the work, where a lot of the work is actually done, is transforming these archetype designs into models of the archetype designs. And this is done by our various teams of analyst specialists. We had specialists in wood and masonry and steel. Each team worked on a different type of seismic system. They created numerical models of archetype designs, and they analyzed them using the methods of P695. FEMA P695 was developed about 15 years ago to evaluate the collapse performance of a new seismic force resisting system proposed for the code. And the idea was to develop a standardized methodology that would be fair among all different systems that we're proposing to be added to the system and have hopefully collapse performance consistent with existing systems already in the code. It's quite an involved technology. I cannot explain all the details of it. Again, you can look at the P695 report for background in that. One important aspect of this methodology is the nonlinear analysis of these models using what is called incremental dynamic analysis. And the result of that is that for a given model, a set of records, in this case 44 record components, are applied to the model, incrementally increased in their intensity until each of the records causes the model to reach its collapse limit. And the collapse limits are shown in this figure by the red dots. And they occur at response accelerations between, say, 1G and 3.6 Gs, and between drift ratios of, say, 3.5 to 12 over 12%. We use these red dots to quantify the collapse fragility. We use these red dots to tell us something about what sort of displacements the model was going through at the point of incipient collapse. Taking the red dots from the prior figure and plotting them as a cumulative function, you can see the red dots again. These are used in the P695 process, adjusted for spectrum shape effects. That's the difference in the frequency content of the record set we used for analysis and the frequency content that we think best represents the region of interest. That gives us a median collapse value, which when of a log normal distribution, and using a log normal distribution, log normal standard deviation of 0.5, we see a curve here, shown here, which is a log normal fragility curve. And it tells us the probability of collapse as a function of the spectral acceleration at the period of the model. In this case, it shows that at a median acceleration of 3.1 Gs, it shows that the design level for this model was 1.5 Gs. The ratio of 3.1 to 1.5 is called the collapse margin ratio. It's about 2. That's a good one. It shows that down at 1.5 Gs, the probability of collapse is 7.3%. These two metrics, the collapse margin ratio and the probability of collapse given the MCT at given MCE ground motions, are the two metrics we use to quantify collapse on this project. So we are looking at these 3 different systems with different configurations to represent different occupancies. For masonry and steel, we considered commercial, which is very typical for those systems. For wood, we considered single-family dwelling, multifamily dwelling, and commercial properties. We considered heights from 1, 2, and 4 stories. We consider they have different R factors in the code. We considered 2 levels of seismicity, which I'll explain more a little bit later. Archetypes were designed in accordance with engineering requirements of ASCE 710, assuming these buildings are used as risk category 2. That means they're a normal sort of construction. Hospitals would be risk category 4. We're interested in the basic risk category 2. We intend these designs to represent typical modern practice in areas of significant seismicity. So we're thinking that these are the sort of buildings that would be designed today. Configurations selected to be realistic and representative of actual buildings and size. But we actually prepared the designs, which were then turned into models. The archetypes that we considered were single-family dwellings. This is footprint is about 32 by 48, 1 and 2 stories. It's sheathed with OSB shear walls. We also incorporate non-structural walls in the wood models. They're very important to the performance of those buildings. We also considered designs based, archetypes based on conventional construction in accordance with the requirements of the 2015 International Residential Code, as well as engineered designs. Turns out that conventional construction performs just as well as design structures. Multifamily dwelling had a bigger footprint, 48 by 96, 1, 2, and 4 stories. Represents typical sort of townhouses and row houses, apartments. Typically, they have a central corridor. Again, sheathed with OSB. Non-structural walls, again, because it's very important to the performance. Commercial buildings, same footprint, 1, 2, and 4 stories, typical of retail and repair shops. Taller ones, which are not common, 2 and 4 story offices. A key takeaway from the configuration of the commercial buildings is that they don't have a lot of walls, interior walls. So they have much fewer interior walls than the single-family dwelling and the multifamily dwelling wood archetypes, and hence have less help in resisting earthquakes from non-structural elements. Masonry archetypes had the same 48 by 96 footprint, 1, 2, 4 stories, typical of office buildings. The cells of the reinforced concrete, the reinforced masonry, were fully grouted. So they're considered, these are load-bearing walls, fully grouted. This is required in high seismic areas, not necessarily in moderate or low seismic areas. Typical of a lot of these buildings, we use flanged walls at corners, which produced a larger foundation below those at the corners, which helped to resist any potential rocking of this archetype. And last but not least, steel archetypes. We took a look at a little bigger footprint, 90 by 150, 1, 2, and 4 stories, typical of office buildings. The system is X-bracing, as you can see here, 2-story X-bracing in this case. The braces were composed of steel tubes. What's important on this one configuration is that we had single bays of braced frames. There wasn't a line of bracing adjacent to another line of bracing, and hence the foundations could rock, and did in some models. So those designs were then transformed into models, and you can see these in the cartoons. The upper left is a cartoon of a light frame wood model. This is in Timber 3D. This model in the middle is a open seas model of a reinforced masonry archetype. It was developed from a more detailed LS Dyna model of the building from which was deduced the properties of the stick elements that you see in this model. And that was done so that we could have an efficient analysis process. The Ellis-Dyna is more detailed, but takes too long to run. And last but not least, again, the steel braced frame model is shown in the upper right side. Parametric studies. We wanted to take a look not just at the typical representative configuration, which we call the baseline models, but also at variations to test whether and how much the displacement capacity of the model mattered to collapse performance. How much did soil structure interaction matter to the performance of the models? And we looked at some other system-specific issues, but again, those are in the reports, but not going to be covered today. So, drilling down a bit deeper into what we did in terms of observed response and performance benchmarks. What would we consider a model to be? When would we consider a model to be valid with respect to what we saw in terms of earthquake performance in past earthquakes, or perhaps on a shake table? So we wanted to establish some benchmarks that we could use to see if our models are achieving realistic representations of collapse performance. So we start by looking back at what's happened in past earthquakes, and this is a summary of U.S. losses, just a big picture view of what's going on in the last 50 years. This is a 50-year period from 64 to 2014, 50-year period, where it was 50 years prior to the start of the project. But it also was important because it began with the 1964 Anchorage earthquake, which is the biggest earthquake to hit the United States ever. And this is a summary of what's happened in those earthquakes. The fact is not that much. The total number of deaths in those earthquakes is between 300 and 400, but in the case of, say, Anchorage, a lot of the deaths, most of the deaths were due to tsunami. So when we parse out the casualties, we see that, about 100 people actually died in this 50-year window of time in short period buildings predominantly, but only 2 people per year on average. Corresponding dollar losses in terms of 2014 money was about $100 billion worth of loss in these earthquakes. And these earthquakes include the 4 main earthquakes, Anchorage, San Fernando, Loma Prieta, Northridge, but also the other 23 significant earthquakes in the U.S. About $100 billion worth of loss in 50 years, $2 billion per year, which may be compared with the total value of the buildings exposed to these shakes, which is a roughly $2 trillion. So 0.1%, 1/10 of 1%, 1 in 1,000. A relatively small number, particularly in light of the cost of earthquake insurance. But what these earthquakes don't provide is information on the big one. They don't tell us about something that would be akin to the repeat of the 1906 earthquake, or for that matter, Tohoku. So we have to remember these earthquakes are significant, but they're not the worst case. And the worst case will be much worse, but less frequent. So we looked for earthquakes that had information about specific systems. This is a matrix that gives an idea. The most useful was Northridge. The 2 most useful were Northridge and Kobe. We looked at other earthquakes because we needed more information on steel and masonry. By and large, it's hard to find collapses. That's the takeaway from all of our studies. It's hard to find collapses, and it's even harder to find information that will lead to a collapse statistic. Comparing Northridge and Kobe, for example, in Northridge, they're about the same magnitude, about the same exposure, about 3 million people in the greater exposed areas. 60 fatalities, only 20 in a building in Northridge, over 6,000 in Kobe. 1% of the buildings received a red tag even in the strongest shaking in the MMI 9 region of Northridge. More than 20% of the buildings collapsed within 5 kilometers of fault rupture in Kobe. The question is the difference is because the infrastructure, the building infrastructure in Kobe was that much different than, say, that in Northridge? Or was it because the shaking was that much stronger? It's both. And a more detailed look at the buildings in Kobe showed that they were very similar in performance. The modern wood buildings in Kobe were very similar in performance to those in Northridge, but they didn't perform as well because the shaking was that much stronger. So keep in mind that we have not seen, in the U.S. at least, the shaking levels that might occur in other earthquakes. So what's typical damage we looked at? Here's a post-1960. We're interested in post-1960 buildings because we want to not incorporate buildings that are no longer constructed. So a post-1960 two-story home up there with a red tag on it in the Northridge earthquake. On the lower right is an earthquake, a building from the same earthquake where it failed because of a cripple wall. We're not interested in buildings with cripple walls. We don't allow that type of construction anymore. Here's a couple of serious collapses in Northridge. Northridge Meadows apartment complex collapse, killed 17 people. It was about 17 out of 150 people in the building at the time. Woodland Hills apartment complex, same sort of first-story failure. It's interesting to note that the building came down on these cars on the lower right-hand side. The cars were not parked halfway under the building. The building literally moved over many feet before it crushed the cars. So it's evidence of a P delta failure at the first story, which we see consistently in all the pictures data from past earthquakes for these short period buildings. Same sort of failure modes in Japan, a two-story house with particularly vulnerable because its walls are weak and it has a heavy clay tile roof. On the lower right, it's some of the older construction in downtown Sannomiya area of Kobe. Mixed-use buildings, not a lot of walls at the first floor. Again, a soft story. People have their businesses on the first floor and live upstairs. Very typical pictures from Kobe. Same sort of first-story failure due to P delta, or would be a first-story failure if it went farther. We also were informed by shake table testing, which helps to really see how buildings collapse. The figure you see in the upper left is a shake table test at Miki of a two-story modern Japanese house. It was shaken 3 times in a row with the J.R. Takatori record recorded in downtown Kobe, very strong record. After the first shake, it looked like what you see in the picture, which has damage at the first story. It's probably repairable. It's not leaning. Significant damage, though. After the second shake, it was leaning at over 10%. It had gone through a peak drift ratio of 15% without collapsing during the shaking. And then the third shake collapsed it at the first floor. This is the sort of image that we, and sequence of images that we want our models to represent. And in fact, during the original studies, we developed wood models that could actually emulate quite well what we saw on this shake table test in Miki. On the lower right is an image from a shake table test down at UC San Diego. The building was a T-wall structure. It's leaning at over 10% drift, probably more like 15. It has a wall in the back. You can see you can stick your hand through the cracks in the wall. It has not collapsed. The researchers pulled on it to over 18%. It still did not collapse. So the notion that masonry might fail at 2 or 3% is not always true. We took the data from the Northridge earthquake, which was the most well-documented event we had here in the United States. The collapse data was not sufficient, but we had red tag data, so we used red tag data as a surrogate for collapse. We and the red tag data was available from the OES Office of Emergency Services report on the earthquake. We got inventory data by census tract from HAZIS, a earthquake loss estimation technology. We got ground motion data from our ground motion experts at USGS and at those that did work for the Sac Steel project. So for each census tract, we knew the number of buildings, the number of red tags, and the accelerations. The fraction of red tags are the little diamonds. and the horizontal axis is the shaking level, and it gives us a sense as to what fraction of the buildings would collapse as a function of the shaking level. Shaking level, you'll see, goes up only a little over 1.5 Gs, so we're kind of limited in the shaking level. It suggests that on average, not more than about 1% collapse rates on average for these buildings. The highest collapse rate was actually around 2.5%, which is typical of the census tract where the Northridge Meadows apartment collapse occurred. So on the basis of this information, we set up some benchmarks. So what did we learn from our observed performance? First story collapse failure mode, very common, typical failure mode. Large lateral displacements at incipient collapse, even for structures that are not wood. Low probability of collapse for MCE ground motions, where MCER ground motions, maximum considered earthquake ground motions, are defined by 1.5 Gs. That's about the level of the shaking we've seen in the U.S. From that, we set some benchmarks. For one-story buildings, we said that our models should not be predicting over about 2% collapse at an MCE level of 1.5 Gs, and two-story buildings or greater should not have more than a 5% collapse rate from our models, where the 5% rate was determined based by looking at the collapse rate, the red tag rates for two-story and greater buildings, which were typically 2.5 times those of a one-story structure. So two-story and greater, 2.5 times more likely to collapse or get a red tag than one story. So these are our benchmarks. We use these to judge whether our models were doing a good job of emulating what we've seen in past earthquakes. So what about the archetypes, parametric studies, and findings? So just to rehash, we're going to be talking about these three models, these three seismic force resisting systems. Excuse me. They represent modern code compliant construction, the 1, 2, and 4 story heights, different occupancies at least for wood, and two seismic levels of 2 different levels of seismic shaking. We use the basic seismic level of P695, which is 1.5 Gs at short periods, which is about all we've ever seen. But we realized that that's not the worst case, and nor is it what is required for design. The higher levels are required for design. So we bumped that up by 50% and called it very high seismic. So we tested all of our models with 2 levels of shaking, high seismic and very high seismic. Very high seismic being having a short period acceleration of about 2.25 Gs. Why is this very high seismic thing important? Because approximately 25% of all the buildings in California, Washington, Oregon, and Washington, that's the western U.S., are located at sites where the short period accelerations exceed 2 Gs. So this is not an uncommon seismicity in the western United States. It's roughly over 3 million short period buildings are going to see or should be designed and will potentially see ground motions in excess of 2 Gs at short periods. So enumerating our various parametric studies, we first and foremost want to look at baseline studies. That's where we have the best and most representative models of the seismic force resisting system of interest, both designed for both high seismic and very high seismic, and likewise tested using high seismic and very high seismic ground motions. We also wanted to look at the displacement capacity because we could see how important that was and how it had not been well understood in past studies. We also wanted to see if soil structure interaction was going to make a big difference in the collapse performance of these buildings. We did a lot of other things that were specific to certain systems, but I'm going to actually not use that information because I want to look at the studies that were common to all 3 systems. So, skipping now through years and years of work and literally tens of thousands of analyses, moving right to a summary of results. As I said before, we're investigating the variation in the collapse performance of typical representative archetypes. Everything we did, we wanted to use best estimate properties and best estimate behavior. And in the case of buildings like wood, we incorporated non-structural finishes because they really mattered, and wood structures typically have non-structural walls in them, even if they're not allowed at this time for design. So again, moving right to a summary of some of the results of particular significance. These two plots on the left, on the right, are on the bottom a summary of results of prior studies that would suggest, at least some of the studies would suggest, that as the period got shorter, the performance got worse, which is what everybody believed. Our models suggest just the opposite. As the period gets shorter, and this is in the upper right-hand side, as the period of the model gets shorter, the performance gets better. So we reversed the trend. We found out it was particularly important. In all cases, the failure mechanisms of our study were based on first-story failure and P-delta failure at the first story, and incredibly important to incorporate P-delta in the modeling and analysis of these types of buildings. So given with improvements in all of the models, more realistic models, better estimations of displacement capacity, we generally could hit those targets. We could generally hit the 2% target for one story, generally hit the 5% target for the taller buildings, taller models. Didn't do very good with the commercial buildings because they didn't have enough walls. They were particularly weak, so we were not able to emulate collapse, these low levels of collapse for commercial buildings where they were inherently very weak. So again, looking at some results from the prior slide, if I put the prior studies results on top of the studies of this project, and it's a bit of a mess. I'm plotting collapse probability as a function of period. It's not real clear what is going on, and that's because period is really not the issue. Strength is the issue. If I replot these points as a function of the strength of the model, then there's a clear trend that the stronger the model, the better the collapse performance. And whatever else is difference between prior studies and these studies, that is true for both. So first and foremost, the most important parameter in determining collapse performance is the strength of the model. And when I say strength, I'm talking about the strength of the model. If you push the model over sideways, what is the peak strength of the model at the point it reaches full yield? This is the definition of V max over W. So key findings for high seismic archetypes also apply to very high seismic. The same failure mechanism, same P-delta failure. However, the performance is not as good. The collapse performance is worse for an archetype designed and evaluated for very high seismic than for high seismic. In other words, we increase the design forces 50%, and then we evaluate the structure for 50% more shaking, and it doesn't perform as well. And the reason is that when we design a structure for 50% more force, it doesn't necessarily get to be 50% stronger because of other influences. In the case of wood, it's because the non-structural does not scale up with the design level. And in the case of the other systems, it's because of design efficiency. So as I said, for wood, it's because of the non-structural walls not getting bigger when the structural walls get bigger, hence less help from the non-structural for very high seismic. And then for the other systems, we found that what was happening was that as you move to higher levels of design, the designer was becoming more efficient in the use of the materials. The wall cross-sectional area was getting less for masonry. Brace sections were becoming closer to the limit allowed by the design-based shear. So for all these reasons, very high seismic performance is worse than high seismic performance, all else equal. So we did a lot of studying of displacement capacity because this is the new addition to all this work, is pushing the displacement capacity of these archetypes out to a more realistic amount of drift ratio before the models collapse. And it's motivated by what we see on shake tables. It's motivated by those pictures I showed you earlier. We find it has a really significantly enhances the collapse performance by considering larger amounts of displacement before the building has a P-delta collapse. So in the case of light frame wood models, we added a plateau to the theoretical nonlinear backbone curve that was developed by the Curie Caltech Wood Project. And this isn't really a new idea. It's something you see in the modeling of elements within ASCE 41 for evaluation of existing buildings. There's very little data on what this actual strength is. It accounts for, it's not just the strength of the wall of an individual wall, it's the collective strength of the structure, out of plane elements, non-structural elements. It accounts for a lot of things in real buildings that you don't get a measure of when you test an individual structural element. This plateau was set in this project at 30% of the peak strength, and we tested it for other strengths to see how much it mattered, and it, of course, matters a lot. We also tested this displacement capacity on masonry by considering different slopes, post-peak strength slopes to the backbone curve. These are backbone curves that were developed from the LS-DYNA model. A little cartoon of the LS-DYNA model is shown in the bottom, kind of green and black. You can see the individual cracks in the walls. It was an incredibly detailed and sophisticated model, which could be used to develop the nonlinear response behavior of that particular model, calibrated against actual test data. This is test data that goes out, in this case, out to 12% or more drift ratio. Get the model. First step was to get the model, the sophisticated model, to match that, then make a simpler model, which is shown in the top curves, and then we varied the slope of the post-peak slope of those models, and again found that the flatter curves, post-peak curves that didn't decay as fast, obviously had better collapse performance. So what we found was that the second most important parameter to strength in the performance of these short period buildings, perhaps any building, is the displacement capacity at the point of incipient collapse. And the reason is, as I've said before, as you add this strength, the additional strength fights the P-delta collapse. The more residual strength you have, the further you go before P-delta collapse occurs, and the stronger the shaking must be, and hence the smaller the probability of collapse would be. So we have a problem in the fact that we don't know much about this. We have a profound lack of data, and so this is the biggest source of uncertainties in any models right now, and it's because we have this profound lack of test data at very large displacements, something that we will recommend research to improve upon. So the other very important study that we looked at was cell structure interaction. We wanted to investigate cell structure, both inertial and kinematic effects, and foundation flexibility. To make this study, we took a model, any model of a wood building or masonry building, and underneath the model, we would either put rigid connections, so as if it had no flexibility at the base, or we put in nonlinear soil springs and dash pots to model the inertial effects of soil structure interaction, and then to account for kinematic effects, which is the filtering effects of at high frequencies. It was akin to what used to be called base slab averaging, or Newmark's tau effect. That was done by actually taking the earthquake records and Fourier transforming them, removing the high frequencies, inverse transforming them. So these are records were modified to remove the high frequencies, and we ran with those modified record sets and with all the cell structure modeling with springs and dash pots. We compared the response of the structures with the soil structure modeling with those without the soil structure modeling, and the conclusion was that nothing much mattered. We found essentially the same probabilities of collapse for the wood structures and for the masonry structures with or without the modeling of the soil structure interaction. An exception to all this was that for when we modeled the steel braced frame with this SSI springs and dashpots, the individual braced frames could rock and did rock on their individual foundations because the braces were very strong and essentially the soil gave before the brace yielded. Interestingly, though, the probability of collapse was about the same, whether it was a failure mode due to rocking, causing excessive displacements in the superstructure, or whether it was failure of the brace on a rigid base, causing excessive displacements in the superstructure. So about the same probability of collapse, although very different failure modes. So we suggest that any reductions in the base shear of short period buildings would be ill-advised, because in fact we don't see that soil structure interaction actually affects the collapse performance or improves the collapse performance in any significant way. Exceptions to this would be buildings with a very large footprint, we're talking about hundreds of feet, and buildings with very deep foundations. Of course, most short period buildings don't have 3 stories of underground parking, so they don't have deep foundations. So we basically found that soil structure interaction was not the reason that short period buildings do well. Along the way of this process, we looked at, we backed up and said, we had this notion a long time ago that short period buildings were supposed to be worse because some prior theoretical studies had found that systematically the shorter the period, the worse the performance. And this seemed to be very contradictory to what we were now finding out. So we said we should look into this and find out what causes this and what is the root cause of the differences in those prior studies and our current studies. What makes the big difference? And I'm referring to studies before the P695 technology. We're going back 30 years or 40 years now, when researchers were using elastoplastic systems analyzed with a lot of different earthquake records. So we first compiled some information on these prior studies. The original work in this area can be dated to that of Letsos and Newmark, 1960. So we're talking 60 plus years ago, when they talked about how to conceptually equate an inelastic system to an elastic system. Then there was but back then there was very few records. As the records poured in, researchers had a wealth of earthquake data to run through models. A lot of different researchers took single degree of freedom systems and ran the records through those systems and generally found the same sort of behavior. And that was documented in a paper by Miranda and Bertero, which I'll show you some results from. All the researchers were finding the same answers because they're based on the same sort of assumptions. Further studies were conducted by FEMA more recently, and then the most recent study was this sameness study that I showed you in the beginning of this little talk. In that study of short period buildings, as part of that study we studied short period buildings, and as part of that study we went back and were able to emulate all of the prior studies using single degree of freedom models. And it's got the same sort of trends. Just quickly, the concepts that laid the foundation for this was this idealization of a yielding system equal to the forces, peak forces in a yielding system, and the peak forces in a system that didn't yield. And this was an idea of equating the energy in the linear system with the energy in the nonlinear system, shown by comparing these shaded areas. And the relationship was such that the ratio of the forces in the two systems, peak force in the elastic system, peak force in the inelastic system, were related by ductility. The ductility defined as the peak displacement of the inelastic system over the peak displacement at yield of the inelastic system. So hence the concept of ductility began, and its importance began, if you will, with this original work 60 years ago. But you'll note that nothing in this figure says that the period, that this applies only to short periods or explicitly, does not explicitly apply to very short periods being, say, worse than other periods. So it doesn't talk about period. But the researchers took the idea of ductility, the idea of peak strength being the strength of the model at pushover strength, the different assumptions of peak strength, different assumptions of ductility, and said, well, and a lot of earthquake records, and said, what are the trends in the performance of systems that have different periods? The notion here being that this would quantify and lead to perhaps a recommendation for R factors being reduced for very short period buildings in proportion to how their period gets shorter, because the performance theoretically was getting worse. So this is the seeds of the idea that really short period buildings perform worse. And this is found by all the researchers that use the same assumptions of a defined amount of ductility. But it seemed to strike us as something wrong. So we repeated in the NIST study in 2012. These studies were repeated. Same findings were found. In the upper, I'll show that the oval circles a result from that NIST study that I'll use in the next slide. But if you look at the lower left-hand corner, it answers the question: what sort of R factor would you need to achieve a certain amount of collapse performance? And in the upper right-hand figure, it says what sort of collapse margin ratio what is the ratio of the collapse margin ratio of the model to the collapse margin ratio that achieves a 10% performance? And it says that for longer period structures, even though it's out to 1 second, it's about 2. But as you get down near short period buildings, at around, say, periods of 2.2 seconds, it says that the ratio of the ACMR to the the ratio of what you're doing, the collapse margin ratio is essentially equal to the failure point, and so implying you should use a smaller R factor and more design force. So we could emulate the results of prior studies, but this is where this study was stopped at this point, and we carried forward with understanding more about what this means. So we said what we need to do is take and first build our own, for this project, build our own single degree of freedom models, emulate everything that was done before in that NIST study, show that we can duplicate their results using the same assumptions of ductility-based collapse, and then turn around and say, no, let's look at it from a different perspective. Let's use drift-based limits. Let's use the drift-based limits that are consistent with what we're doing on this project. And the result is that for ductility-based, we got the same answers. And when we went to a drift-based approach, we got very different trends in the results. For example, the comparison here, the oval now contains a comparison of models that were constructed using single degree of freedom models, constructed and evaluated using the same assumptions of ductility, same results as the prior NIST study. When we turned around and said that the displacement limit should be based on drift, not ductility, we get the blue and black curves, which change both the trends in the collapse performance. Collapse does not get worse at short periods; it may get better even, and it's a much better in general. What is the real reason for this? Why were all the prior studies off base, if you will? And that is because a ductility limit on collapse is incredibly pessimistic for very short period buildings. For example, where the second row, which says one-story models. Here's models. These are single degree of freedom, simple models, have a period of 0.15 seconds. If their yield strength is 40% of the weight of the building, which is very typical, that's the green oval, those models yield at less than 1/10 of an inch, and even with a ductility of 8, they are theorized to collapse at 0.7 inch. No building collapses at 0.7 inch. So using a ductility approach is very pessimistic with respect to the actual displacement capacity of a building, hence very bad collapse performance. In contrast, if we use a drift-based collapse criterion of 7.5%, we get 9 inches. Buildings don't collapse at 9 inches as commonly, as frequently as they would at less than 3/4 of an inch. So we get very different collapse results. The collapse answers for drift and ductility-based assumptions are more alike when you get to taller models where the periods are longer, the yield displacements are greater. In that case, for a 4-story, a ductility of 8 would take you to a 6-inch, 6.4-inch collapse displacement, which is more like the 9 inches based on a drift-based criterion of 7.5%. So the root cause of the difference is that by using an assumption of ductility, of some reasonable ductility, even up to 10 ductilities of 10, it's just very pessimistic with the actual observed collapse performance of short period buildings. It's not a realistic criterion. So in other words, all those studies were grossly over predicting the collapse potential of short period buildings. So all this study led us to a theoretical basis, a better understanding about why the prior studies were not telling us the right story, and that with improved numerical models, especially with larger displacement capacities, we got much better collapse performance at short periods. This study, however, was using single degree of freedom models whose backbone characteristics, nonlinear hysteretic properties, were not representative of any of the seismic force resisting systems of interest. So it's really a conceptual approach, a theoretical approach that indicates why we are getting different answers now than from those studies, prior studies, but doesn't answer really what's going on. One of the nice things that came out of this study was the idea that we had a lot of results, a lot of collapse results. We had models with all different strengths. They're very simple models, but they had all different strengths and all different displacement capacities, and a suite of collapse results. And we said this begs forming a surface, a collapse surface, that says the surface is defined by one of the collapse metrics, say collapse margin ratio, and that would be plotted as a function of 2 parameters, strength on one axis and displacement capacity on the other. And here's a couple examples of those. This is a characterization of those single degree of freedom models that we developed as part of the study of the theoretical basis for the motions. The one on the left is typical of a short one, a period of 0.15 seconds. The one on the right is a taller building, perhaps 0.45 seconds. The surfaces are different because the periods are different. What they say is that the more strength you have, the more displacement capacity you have, the larger the margin, collapse margin, the smaller the probability of collapse. So this notional collapse surface is being used in a current project to characterize the trends in behavior in very high seismic regions, but they have a lot of value to them in characterizing the trade-off between strength and displacement capacity in terms of collapse performance. So you can use them for that purpose. You can say, if I know the strength, I know the displacement capacity, I know my collapse probability, or my ACMR, my collapse margin. You can also use them the other way around. You say, if I were a given amount of displacement capacity and a target collapse performance, I can backfigure from the surface what amount of strength my building should have to achieve that amount of collapse. So these are incredibly useful for performance-based design as a tool to tell the user what sort of strength the building should have for any amount of desired collapse performance. Now, wrapping up in terms of collapse performance, back at the original paradox, we think we've solved the paradox. Restating again the original question, Why do analytical models of code-compliant designs predict high probabilities of collapse for short-period buildings, contrary to the damage observed in actual earthquakes and the judgment of earthquake engineers? As my good friend Bill Holmes said when we began this project 7 or 8 years ago, show me the bodies. And that is largely a reason we think we don't have a problem, because we look at past earthquakes and we see good performance. If we had collapses, if we had collapse issues, we would see a lot more fatalities. We don't. So that's the first item. Second, we see that with these more realistic models, particularly in terms of displacement capacity, we get a much better collapse performance. And in fact, the theoretical insight gained from that single degree of freedom study says that we should see better collapse performance than we had in prior studies. So, and finally, we in general see very low collapse probabilities, similar to what we see in observed in past earthquakes. So we think with all these, we have answered the question that the short period buildings basically are performing well. They are not a particular collapse risk. We learned a lot about how to better model. We learned a lot about what we needed to do. And we also, after 7 years of work, came up with a number of recommendations for improving seismic design, which Kelly Cobean will now walk us through. So Kelly, I'm going to stop sharing.
Thank you very much, Charlie, and I will get my screen going here. And we are ready to move forward. So as Charlie mentioned, coming up with recommendations for improving seismic design out of this big project that looked at a lot of different models and variables and so forth was really a priority. And the full set of recommendations can be found in a combination of Chapter 7 of Volume 1, and those are more of the overarching recommendations that run across the different material types, archetypes, and so forth. But also in Chapter 6 of Volumes 2, 3, and 4, you can find additional recommendations that are specific to the different material and archetypes. So if you're interested, please take a look at those. This presentation is going to focus more on the overarching ones than the particular material specific recommendations. The recommendations that were put together were organized into 3 separate groups thinking about different users. And for improving seismic design codes, those were intended primarily for the seismic code development committees and the standard committees. And you see on the screen a few of the codes and standards they might be going to, along with the different materials. Another set of recommendations is looking at advancing seismic design and analysis practice. And that is particularly geared towards engineering practitioners. And then a third set is really looking at enhanced modeling, testing, and data collection, and the ability to have some of this advanced testing and the modeling that Charlie's been talking about was a very big part of the advancement seen in the project. These are intended primarily for research engineers and academicians. So we're going to start with the seismic design codes and standards and our codes and standards committee. And Charlie has already very nicely introduced this collapse surface concept that came out of the project. And within this collapse surface, the very important variables were found to be the strength expressed as the peak strength of the archetype or the building relative to the seismic weight, and the story drift or the drift capacity. And so these are nicely expressed in these particular surface figures that you see here. And it's felt that these are very important tools to be used in developing codes and standards. And Charlie spoke to a number of ways that these might be used already. One of the thoughts put forward is that they would be very valuable in really encouraging uniform performance across the different systems, heights of buildings, and other variables. And clearly also for those interested in improving performance, this gives important information about how improved performance might be accomplished. Another recommendation that came forward was to consider the actual strength and deformation capacity. Charlie spoke extensively about really getting into the post-peak realm and understanding the strength and the displacement capacity well beyond peak strength. And that was very critical to the results of the project. And so as the concepts from this project move forward to the code and standard committees, it's important to keep in mind that this is important and they need to be looking for that strength and deformation capacity information and incorporating it into future considerations. Another recommendation is to recognize that future refinements in design and construction can affect undesigned overstrength and therefore the seismic performance. It was discussed that all of the different buildings had undesigned strength that very much contributed to the performance. For the masonry buildings, it was that the architectural length of the masonry walls was more than the minimum that would be required for the seismic design, and also the minimum reinforcing added overstrength beyond what the minimum structural design would require. For the steel buildings, what was found was that the braces that were designed for compression and buckling behavior had very significant tension overstrength. And that, along with sort of the rules for incrementing size of the diagonal bracing, contributed significant overstrength. And in the wood buildings, as Charlie mentioned already, all of the finished materials that are put over the wood structural panel shear walls, on the exterior, all of the non-structural partitions. So the reminder to everyone in the codes and standards realm is that strength that is contributing to the performance of these buildings is coming from that undesigned overstrength in addition to the designed overstrength. And as we move forward and think about future designs and criteria for these buildings, that has to be kept in mind as an important source. The next recommendation comes from the concept in ASCE 7 about deformation compatibility and making sure that our gravity systems are able to withstand the drifts that the building is going to see. And what you see here is the incremental dynamic analysis data plotted out. And in this particular case, the mean story drift at incipient collapse is at about 6.5%. And the point that is made here to the codes and standards committees is that that 6.5% is much higher than the drift limits that the code imposes right now. And if we're going to rely on getting the probability of collapse that is indicated by these analyses, that we have to think about what is happening to the gravity systems when they get up to this 6.5%. It isn't clear that we need to go and automatically change the ASCE 7 criteria for deformation compatibility, but it ought to be thought about, and there's probably some further study of that topic necessary to make sure that our gravity systems are still in place and able to function at the kinds of drifts that we're expecting. The next recommendation is talking about increased collapse potential with very high seismic demand. And again, Charlie talked about this already, and the project went and designed buildings for what was labeled high seismic, S sub MS of 1.5, and then ran the analysis with appropriately scaled ground motions and got a probability of collapse. And you see those for a variety of buildings in the green bars on this particular graphic. Then they went back and they designed buildings for very high seismic, S sub MS 2.25G, and then did analysis of those with appropriately scaled ground motions. And the probability of collapse shot up very significantly. So the message is that it appears that buildings that were using the current code and ASCE 7 provisions for in the very high seismic regions might be very much more vulnerable to collapse than the ones in the high seismic. And one of the things to note is that ATC project currently underway is exploring this particular issue as we speak. A few other recommendations here: undertake research to address target collapse probability. Should the conditional probability of collapse be revised to be more in line with empirical experience? Should we be changing the FEMA P-695 methodology? Charlie mentioned that for one-story buildings, the data that was assembled suggested about a 2% probability of collapse and 5% for what is two-story and greater. And that is significantly lower than the current target we have for the ASCE 7 provisions that is envisioning 10% probability of collapse at MCE. So a question to be undertaken there. Second question, should the methodologies for estimating collapse probability be revised to explicitly consider strength from elements not a formal part of the seismic force resisting system? This study is finding that it's the non-designed overstrength that has a huge influence on the collapse results. Should that non-designed overstrength be considered in FEMA P-695 studies in other performance-based studies? Question to the code and standard people. Third one, should target conditional probability of collapse be different for very high seismic sites than for others? Our data is saying the performance there is different, is less than that 10% probability of collapse that is the current target. Do we need to consider and set that differently for those very high seismic sites? And then item number 4 is all of the studies we've been talking about are for short period structures. And what do we need to know about long period structures? And do we need to explore those issues there also? A few other recommendations around the FEMA P-695 methodology. One is that the seismic criteria, the demands from the P-695 methodology are no longer in line with ASCE 7, and particularly ASCE 722 has modified those, and there's a question of whether P-695 in a sense needs to be realigned with where ASCE 722 is at this time. And then the second item has to do with FEMA P-695 and the very high seismic again, the shaking of sites close to major faults. And that is a question that should be asked regarding the P-695 criteria. Charlie talked a bit about the soil structure interaction studies that were done as part of the project. And the recommendation is that the ASCE 7 provisions for soil structure interaction should be reevaluated based on the outcome of this project. What you see on the screen right now is pushover curves that come from buildings modeled both with and without soil structure interaction. And For 2 of the 3 systems, the studies suggested that there was no change in performance if you took a building that was designed as a fixed base building and then ran it through the analysis as a fixed base building, and then ran the same building through the analysis with the soil structure interaction modeled for both a stiff soil site and soft soil site. So if the same building does not have any change in performance, whether it's on a fixed base or on a modeled soil, but our ASCE 7 provisions right now tell us that we can reduce the base shear if it's on a has soil structure interaction behavior, then that suggests that buildings designed with that reduced base shear will likely not perform to the intended criteria, that 10% target that we're looking for. So recommendation that that be looked at and to make sure that we're on firm ground with that. So now we're going to move on to a couple of recommendations for the practitioners around seismic design and analysis. And the first one is really a caution. We did find in the project that a lot of undesigned overstrength is coming from some of the elements in our systems. And if those elements are providing a lot more strength than our design is requiring, we know that they're going to be attracting a lot more force. And we want to make sure that that doesn't result in unintended failure modes. So for example, in this illustration here, the L-shaped corner wall is attracting a lot more force than is accounted for in our initial seismic design. And because of that, things like the load path connections between the diaphragm and that wall will experience higher forces, and that could lead to the load path connections being a weak link. So the designer is cautioned where you have overstrength, you are likely to attract higher forces, and you want to make sure that you're not getting unintended weak links. Another caution that came out of it to designers, and Charlie talked about the concentric braced frames and the fact that once we went to the soil structure interaction models, we introduced foundation flexibility. And as we did that, we found that the braced frames were in a lot of cases rocking. And that rocking behavior is implying not only flexibility, but also some hinging in the foundations. And so being aware that that rocking may occur, we want to make sure that the design is a safe design when the foundation rocking occurs. And we also believe there should be some thought around, if rocking is occurring, if foundations are hinging, do we have the proper design in the foundations to accommodate that hinging and to allow the foundations to perform as necessary in order to get appropriate collapse behavior and meet our performance targets. So be aware of that performance. And finally, we have a few recommendations around modeling, testing, and data collection for our research community. And this has been said several times, but it's worth saying one more time. We really need to develop cyclic testing protocols to help us take our tests up to incipient collapse or actual collapse. This information that we get is critical to the realistic modeling of the collapse performance and has a very significant impact on the collapse probabilities that comes out of it. You're seeing here the very nice work that was done by Benson Xing and his team down at UC San Diego. But testing out to very high drift levels is very important. Developing testing protocols to guide that testing to that extreme level is very important. An emphasis on shake table testing to large displacements, and each of the three material groups came up with the same recommendation and emphasized the need to go out to very large displacements on the shake table and to look at bidirectional ground motions. Those were found to be very important to capturing the performance versus unidirectional ground motions. Where shake table testing is not possible, and it's understood that it is large projects, very expensive projects with shake table testing, there is an encouragement really to think not about small component testing, but with the other testing being assemblies, and an important focus on realistic boundary conditions that will really make sure that we are seeing the appropriate behavior of the component and not one that is changed by not having the appropriate boundary conditions. And one final recommendation, this project spent a lot of time, and Charlie talked about going through the available data from past earthquakes. And it's very important to have thorough data that looks at an area and goes very carefully, not just through damaged buildings, but through the entire building stock to quantify the portion of the buildings that are damaged, the extent to which they're damaged, the mechanisms of damage. And so the recommendation is that we really do have both protocols put in place and organizations that are ready to be sent out and rapidly get out and capture the data that we need in order to judge where our computer modeling performance is relative to the actual performance, and give us that basis for understanding performance to date, and being able to understand where performance and where modeling should go in the future. So with that, I would like to turn it back over to Justin to close out the webinar.
Great, thanks, Kelly. On behalf of FEMA and the Applied Technology Council, I'd like to thank Charlie Kircher and Kelly Cobean for their presentation. And thank you to everyone for joining us today. For those who registered and attended, expect to receive a follow-up email with links to the recording of the webinar and to a participant survey. Please provide your feedback because we use that information to improve our webinar program. A separate email containing a professional development hours certificate and responses to questions posed today during the webinar will be distributed within 4 weeks. This concludes the webinar on FEMA P-2139, short period building collapse performance and recommendations for improving seismic design. Have a great day.